In this example, we will look at how to find the Thevenin equivalent of a circuit containing both independent and dependent sources. In this given circuit of interest, the load resistor is already removed and the terminals of interest A and B are marked. We can see that this circuit has two independent voltage sources, and then this is the dependent source in the circuit. The symbol for the dependent source has a plus minus inside it. So this is a dependent voltage source, and we can see that the magnitude of this dependent source is in terms of a circuit voltage. So this is a voltage controlled voltage source. Let's see how we can find the Thevenin voltage and the Thevenin resistance for such a circuit. First, let's find the Thevenin voltage VTH. The Thevenin voltage is the open circuit voltage between the terminals of interest. Thus, in this given circuit, the Thevenin voltage VTH is the voltage between terminals A and B. We can use any circuit analysis technique to find VTH. First, let's use node voltage method. So let's apply the node voltage method here. We can ground this node, and then this is a good choice for the ground because then at this essential node the voltage is known and it is 100 volts, and this is because we have an independent voltage source directly connected between ground and this node. This leaves this node as the only remaining essential node. So denote the node voltage here as Vx, and we can apply Kirchhoff current law to this node. So applying KCL here, what we get is Vx minus 100 over 4. So this is the branch current through the 4 ohm resistor. Next, through this 4 ohm resistor, voltage at this side is Vx, and voltage here is 20 volts because we have the 20 volt independent voltage source directly connected between here and ground. So this branch current is given by Vx minus 20 over 4. Along this branch, we can see that there are two 4 ohm resistors in series, and voltage at this end of the resistor is 100 plus V phi. So we can use this fact to write the expression for this branch current as voltage at this side, which is Vx, minus voltage at the other side of the two 4 ohm resistors, and this is 100 plus V phi divided by 8 is equal to 0. In this case, although we have 3 voltage sources in the circuit, there is no supernode formed. We have one dependent source, so we need to write the dependent source constraint equation, and that means expressing V phi in terms of node voltage Vx. We can see here that V phi and 20 volt drop add up to Vx if we go along this branch. So this means the dependent source constraint equation is Vx is equal to V phi plus 20. So here we have two equations and two unknowns, and we can solve to show that Vx comes out 80 volts and V phi comes out 60 volts. So the node voltage analysis is completed, but we are interested in the open circuit voltage VTH, and this can now be found using the node voltage Vx. In order to do that, let's define this current I, and this current is entering the 4 ohm resistor at this end, so it is marked positive, and it is leaving the 4 ohm resistor at this end, so it is marked negative. If we apply Kirchhoff voltage law along this path, we can see that minus plus, minus plus, minus plus, these polarities add up. So VTH is given by 20 plus V phi plus 4 times I. Now this current I we can find by applying Ohm's law to the series combination of these two 4 ohm resistors. So this current I can be written as voltage at this side. So voltage at this side is 100 plus V phi minus voltage at this side, which is Vx, divided by 8. And substituting the value of Vx and V phi here, we can show that this comes out 10 amps. So substituting this value of I here, what we get is 20 plus 60 plus 4 times 10. This comes out 120 volt. So this means the Thevenin voltage is 120 volts for this circuit of interest. We can also find the Thevenin voltage using mesh current method. So in this given circuit, the Thevenin voltage is the open circuit voltage here. To apply mesh current method, we note that there are 2 meshes in this circuit. So suppose we assume mesh I1 and mesh 2 with current I2. Now we can apply Kirchhoff voltage law to this circuit. So this circuit has voltage sources only. Voltage sources cannot give rise to a super mesh. So we don't need to check for the possibility of a super mesh. So let's apply Kirchhoff voltage law to mesh 1 starting at the 100 volt source. So we get minus 100, and then we have 2 currents through the 4 ohm resistor. So this is 4I1 minus I2. We give precedence to I1 because we're writing KVL for mesh 1. And then moving on to this resistor, we get 4I1. And then for this 20 volt source, I1 is entering the terminal marked plus, leaving the terminal marked minus. Going from plus to minus is a voltage drop. So this is written with a positive sign under passive sign convention. Similarly, for mesh 2, we have minus V phi and then 4I2 and then another 4I2. So current through these 2 resistors is only I2, and through this last resistor we get 4I2 minus I1 is equal to 0. Because the circuit has a dependent source, we need to express V phi in terms of mesh currents. So V phi is the voltage here. Applying Ohm's law to the 4 ohm resistor, V phi is equal to 4 times I1. So we can see that we have 3 equations and 3 unknowns. So these can be solved to show that I1 is 15 amps, I2 is 10 amps, and V phi is 60 volts. So this completes the mesh current analysis. However, we still have to find the voltage V Thevenin. So this can be done by assigning this polarity to the voltage drops. Now applying Kirchhoff voltage law to this path, we can see that V Thevenin is the voltage drop across this 4 ohm resistor, which is 4I2 plus V phi plus 20, and substituting values, this gives I2 is 10 amps, so 4 times I2 is 40 plus 60 plus 20 is 120 volts. Thus, no matter what circuit analysis technique is used, we arrive at the same answer. Next, we look at how to find the Thevenin resistance. When the circuit contains both independent and dependent sources, we can use either the circuit analysis method, referred to here as method 1, or a combination of method 2 and 3. First, let's see how we can use the circuit analysis method to find Thevenin resistance. So we have previously found V Thevenin to be 120 volts. So according to the circuit analysis method, we need to short circuit the terminals of interest and find the short circuit current, and then the Thevenin resistance is V Thevenin over I short circuit. For this subtask of finding the short circuit current, again, any circuit analysis technique can be used. For instance, we can use node voltage method, which is very efficient for this given circuit. We can ground this node. Then the voltage at this essential node is 100 volts. Because of this short circuit, the voltage at this essential node is 0 volts. So we are only left with one essential node where the voltage is not known. So denote that by Vx and assume branch currents are flowing away from the node. We can now write the Kirchhoff current law equation here. So this gives Vx minus 100 over 4 plus Vx minus 20 over 4, and through this last resistor, Vx minus 0 over 4 is equal to 0. So here we have only one unknown variable, and this equation can be solved to show that Vx comes out 40 volt. After finding Vx, we can now find V phi. So we can see that Vx is equal to V phi plus 20. So this implies V phi is equal to 20 volts. Now the node voltage analysis is complete, but we still need to find I short circuit. And this can be done by applying Kirchhoff current law to this node. So let's identify two branch currents, Ix and Iy. And this branch current is ISC. This branch current Ix is given by Ix is equal to Vx minus 0 over 4. So substituting values, we get 10 amps. Current Iy is voltage at this side minus voltage at this side for this 4 ohm resistor. So this is 100 plus V phi, which is 20, minus 0 over 4. So this gives 30 amps. Now applying Kirchhoff current law to node A, sum of currents entering Ix and Iy is equal to I short circuit. So this means I short circuit is Ix plus Iy, which is equal to 40 amps. And now R Thevenin is given by V Thevenin, which is 120 over I short circuit, which is 40. So this gives 3 ohm. So this illustrates how to use circuit analysis method to find R Thevenin for a circuit containing both independent and dependent sources. We can also use combination of method 2 and 3 to find the Thevenin resistance. This method says first deactivate independent sources and then apply a test source and find this ratio Vt over It to get the Thevenin resistance. So first we need to deactivate the independent sources. There are two independent sources in this circuit, and in order to deactivate an independent voltage source, we replace the voltage source by short circuit. However, for the dependent source, we cannot zero it and we have to leave it as is. So redrawing the circuit by zeroing out the independent voltage source, we get the following circuit. So the two independent voltage sources have been zeroed out, and we have the dependent source which we cannot zero, so we need to leave as is, and then the remaining resistors. So this is the first step to obtain the circuit by deactivating the independent sources. And now we need to apply a test source to the terminals of interest. We can apply a test current source or a test voltage source. Let's use a test voltage source. So we connect a test voltage source, and for its magnitude we can arbitrarily choose any value. Suppose we choose 1 volt, and then we have to find this current IT, and the ratio of VT over IT will be the R Thevenin value. Now for our circuit analysis task is to find IT. Again, any circuit analysis technique can be used. Suppose we use node voltage method. Let's see how we can use node voltage method to find IT. So we can ground this node, and that means the voltage here is 0 volts, and the voltage at this node is 1 volt because the test source is directly connected between ground and this node. So this leaves only this as the remaining essential node. Now from our circuit of interest, the voltage drop here is V phi, which is the magnitude of the voltage controlled voltage source. So looking at this circuit, this parameter V phi is actually the node voltage here, because the node voltage here is the voltage drop across the 4 ohm resistor. So we can use the symbol V phi for this node voltage. And now we can apply Kirchhoff current law and write the equation at this node. So this gives V phi minus 0 over 4 plus V phi minus 0 over 4, and then through this resistor the voltage on this side is 1 volt. So V phi minus 1 over 4 is equal to 0. And this equation can be solved to show that V phi is 1 over 3 volt. Once we determine V phi, we can now determine IT. And in order to do that, let's define this branch current, which we can call IY, and this branch current, which we call IX. Applying Kirchhoff current law to this node, sum of currents entering IT is equal to sum of currents leaving, which is IX plus IY. And these branch currents can be written because we have already found the node voltage V phi. So IX is the current flowing in this direction through the 4 ohm resistor. So this is 1 minus V phi over 4. So 1 minus V phi over 4, and IY is the current through this branch, through this 4 ohm resistor. So it's voltage on this side minus voltage on this side, which is also V phi because of the dependent source. So this is 1 minus V phi over 4, and the value of V phi is already found. So substituting values, we can show that this comes out 1 over 3 amps. And now we can substitute to find R Thevenin. So R Thevenin is VT over IT. So this is 1 over 3, which again comes out 3 ohm. So this shows how to use combination method 2 and 3 to find R Thevenin for a circuit containing both independent and dependent sources. Finally, this is the summary result. From the point of view of terminals A and B, these two circuits are equivalent. So this circuit containing 2 independent voltage sources, 4 resistors and 1 dependent source is equivalent to this simplified circuit with VTH 120 volt and RTH 3 ohm.